Hi, I'm Asif Azad Prince. These are my project partner, Chaudhary Muhammad Abdullah Mahbub and Mirma Shakar Kundu. Today we are presenting the design and analysis of a hybrid power system for McCallum and Canada. We are supervised under Professor Tariq Iqbal from Memory University of Newfoundland. Energy is crucial in generating wealth, social development, improved quality of life in all developed and developing countries. Global energy demand is likely to grow faster than population growth. Almost 80% of world's generated energy demand is being fulfilled by fossil fuels. As a result, the reserve of fossil fuels is reducing rapidly, and fossil fuels consumption increases carbon emission, which escalate the average temperature of our surroundings. In this situation, experts are paying attention to renewable energy resources, resulting in carbon emission reduction and reusing natural energy resources to generate electricity. Renewable energies are energy sources that are continually replenished by nature, derived directly from the sun as a thermal, photochemical, and photoelectronic, indirectly from the sun as wind, hydropower, and photosynthetic energy stored in biomass, or from other natural movements and mechanisms of the environment, such as geothermal and tidal energy. Renewable energy sources are not only limitless energy sources in the future, but also environmentally friendly and environmentally sustainable due to ongoing depletion of fossil fuels and rising energy demand. The area we chose to implement the project, this area is known as McCallum, which is part of one four Atlantic province of Canada, Newfoundland and Labrador. It is located on the southern shore province. There is a small community of 73 people in this area. Most of them use ferries, speedboats, seaplanes as modes of transportation. As this place is totally isolated from mainland, they do not have grid connectivity. Literature review. Our technological change is unavoidable as it continues to expand and impact the world's major infrastructures. Floating solar panels are innovative approach to using photovoltaic modules on water infrastructures to conserve land while increasing module efficiency. After doing some literature from the author Abu Hena Shatil, he designed a floating solar panel for Cholonbil, Bangladesh. They investigated installing floating solar panels in Cholonbil, Nator, Rajshahi. The comparison of ground-mounted panel, floating panel based on electrical factors such as output power, cost is also seen throughout the experimental setup. After the analysis, it is found that the energy conversion cost in floating panel setup is over 5-7 cents per kilowatt hour, which is quite acceptable. Another author, Sachin J.M., he reviewed the floating PV panel installed in India. This paper focused on floating PV technology, described the types of floating PV plant along with studies carried out on some floating solar plants. Additionally, the feasibility of putting 1 megawatt floating PV plants at the Kishore Sagar and Kota barracks in Kota, Rajasthan. The two plants potentially energy output, the water consumption from the evaporation, and decrease in carbon dioxide emission are all calculated in the study. Another author, Farid of K, he outlined a model and control scheme for solar-powered freestanding microgrid. To test the effectiveness of the microgrid, the photovoltaic panel converters and the storage device are researched models. From Martinez, he designed and analyzed a floating photovoltaic-based energy system with underground energy storage option for remote communities. The resilient solar energy-based system with energy storage option proposed in this study is specially engineered to produce electricity, heat, cooling, hydrogen, and ultimately ammonia. An anion exchange membrane electrolyzer, a pressure swing adsorption, air separator with ammonia reactor, and a heat pump are all integrated into floating photovoltaic plate. From Manoj Kumar, uh, This study presents an overview of various design and construction tactics along the offshore PV technology and status of FPV systems. The specific design and structure of FPV effect is output generation, durability, and investment cost. The chosen site, McCallum City. This area is surrounded by Atlantic Ocean. This area is known as McCallum, and which is a part of one of the four Atlantic provinces of Canada, Newfoundland and Labrador. It is located on southern shore of this province. This is a small community of 73 people in the area. Most of them use ferries, speedboats, seaplanes, and other modes of transportation if they have any. As this place is totally isolated from the mainland, they do not have any grid connectivity and any other grid facility from government. So they have their own fossil fuel-based generators, and it's not enough to meet the daily needs. Because there is a hospital that which only runs on only 2 days in a week due to lack of electricity. And this kind of uncertain situation is harmful for the community. And the school it also cannot run properly in like 5 days in a week due to the electricity. There is not enough electricity for all of them. Moreover, due to unstable resource of electricity, most of the families struggle to do their household activity, and they also have to take deliveries from other fossil fuels from other side of the sea. So they use ships and other marine vehicles to transport those fuels for their generators. But if the weather is bad in the sea, the delivery shipments will be stopped for like uncertain amount of time. And for them, they can be face some like massive electricity. There can be some massive electricity lackings in the community. The reason for choosing this solar panel. Considering the location, we could use wind turbines. However, for the gusty wind and the seashore area, these turbines may get damaged. Moreover, there is no water flow from upstream and no chance of building dams. This is why constructing a hydropower system will be much more expensive for this small community. The geothermal and the biogas process will not be that much effective for this location. For these reasons, we only consider solar power to regenerate alternative energy for that community. Solar power is now a sufficient source of renewable energy. It is utilized for various purposes, including commercial applications, solar heaters, and pumps. Solar electric helps to alleviate the possibility of integrated grid power. This area is surrounded by tall mountains, so no availability of plain surface hinders setting up the conventional solar panels. In this scenario, a floating solar panel system will be better option, different from ground-mounted PV. A floating construction is called pontoon. Uh, the base of pontoon allows it to hold a hefty load while floating in water. The framework is built so that it can support several panels. The PV models can be installed thanks to the floating framework. It can take so many PV models on it. It's really stable and it's really feasible for that. The mooring structure, it's permanent structure used to anchor the floating structure so that it cannot move around freely on the water. So it's connected in some point in the water. So it's only have only few portion of the water to it cannot move, but it's not can really move freely. It's also already constructed to the shore by an anchor. And it's also secured by that anchor to the shore, so it does not float away anywhere in the river or the sea. So this enables the regulating water level changes while keeping it position facing south. From now, my next group member, Georgia Mahbub, will continue. Thank you.
Hello, Professor. This is Chaudhary Muhammad Abdullah Mahbub, welcoming you again in our presentation. And I'm going to start with the calculation methodology. So the calculation starts with the estimation of total daily electric consumption of that rural community. We have collected the annual energy consumption data of that area from Newfoundland and Labrador Hydro, and calculated approximate daily consumption. After that, the environmental resources have been analyzed, such as solar irradiance and temperature of that area. Then, the entire system has been designed initially in the Homer Pro optimization tool, and after that, we have designed the same system using PV-Word online simulation software and MATLAB Simulink to compare the simulation results. And you can see here our calculation algorithm, and it depicts the sequential steps of our calculation procedure. Let's see the present energy scenario and load demand. According to our collected data, annual load demand for McCallum Island is 360,000 kilowatt hour per year. So approximate daily load consumption is 986 kilowatt hour per day, having a maximum peak load of 149 kilowatt. And currently this area is being powered with three diesel generators, each having 150 kilowatt of capacity. And to fulfill this load demand, these three generators consume approximately 128,959 liters of diesel per year. Here we can also see the monthly load profile, and from this graph we find the average load consumption during the winter, that means in the month of November, December, January and February, are higher than others. And this excess consumption is obviously because of the heating purpose in cold winter. Now the environmental resources. So before installing any renewable energy generating system in a specific place, the weather data and geographical conditions must be considered. That's why the solar irradiance and temperature data has been obtained from the NASA Prediction of Worldwide Energy Resource database in Homer. The annual average solar irradiance in this area is 3.17 kilowatt hour per meter square per day. And this is not bad for a PV module to extract the maximum power. And from the graph that shows the average solar irradiance data in every month, we can see the irradiance is generally high during summer, with the highest in June and the lowest in December. And the annual average temperature in this area is 4.41 degrees centigrade, having the peak in the summer, obviously. And however, the graph shows the peak rise of temperature is in the month of August, and the lowest is in February. Let's have a look to our system components. The design of the floating solar photovoltaic system has been done by choosing suitable components using the energy equations based on the available resources and load estimation. However, and the prime components are solar photovoltaic module, battery storage, converter, and existing diesel generators. And you can see the Homer diagram of our proposed system. And this system contains two bus. One is AC bus and one is DC bus. And the diesel generators are directly connected to the AC bus, but the battery storage and solar photovoltaic modules are connected to the DC bus, and these two buses are interconnected through a DC to AC converter. Here are the specification details of our system components. Firstly, table 1 represent the details of our photovoltaic module. For this project, we have chosen a photovoltaic module from Canadian Solar Company Limited, and the rated capacity of this photovoltaic module is 0.315 kilowatt, and it has a operating temperature of 43.9 degrees centigrade, having a module efficiency of 13%. And the expected lifetime of this PV module is 25 years. Now, table 2 shows us the details of our storage system. and we have chosen the battery from Trojan SAGM, and the nominal capacity of the battery is 1.39 kilowatt hour, and it has an ampere rating of 116. It is a 12-volt battery, and it has the maximum charge current of 21 ampere, and maximum discharge current is 263 ampere. And table 3 gives us the details of the converter and existing generators. So we have chosen the converter for our project, and that is a Sine XL 150 kilowatt DC to AC converter. And these are the existing generators from Generac Limited. Those three generators all are 150 kilowatt. Now the Homer simulation. Homer, a computer model developed by National Renewable Energy Lab and distributed by the Homer Energy. And this software is used to design our proposed system. From the Homer simulation, we find that the system is producing 4,77,944 kilowatt hour electricity per year. And out of this total production, 3,65,350 kilowatt hour is producing from the PV modules, and that is exactly 68.7% of the total generation, and the rest is coming from the diesel generators. So our renewable fraction is 68.7%. In that case, we can say with the new floating solar photovoltaic energy system, we can cover almost 69% of the energy demand of this community. Now, the simulation from the PV works, and PV is another helpful map-based free online tool for analyzing solar sites, especially in the USA and the abroad as well. Here, we use this tool to verify the PV module output that is found from the Homer simulation, and that was 365,350 kilowatt hour generation of per year. Now, if we see the result from PV watts, we can see the yearly generation is 340,838 kilowatt hour, which is slightly less than the Homer result. But this 6% difference is negligible, as we consider many loss factors here, like snow effects and others. However, Homer also shows a little bit excess energy that we may consider as different types of system loss. Now, I am welcoming my next group member, Mrimma Shikhar Kundu, to conduct our next part and ultimately the last part of our presentation. Thank you.
Thank you so much, Chaudhary. This is Mrinmar Shekhar Kundu presenting the terminal part of our project. In this part, I will talk about the MATLAB simulation. We have implemented our proposed system in MATLAB to analyze its output. Here we have selected Canadian Solar CS6U PV panel, which is of 350 watt. To meet up our total consumption, we have assigned 33 strings of PV module in parallel and 34 strings in series. We have also considered the average temperature of that location, which is 4.41 degrees Celsius at the time of simulation. In this simulation, we have measured total generated power through the bus bar as well as the calculating voltage and current. In both process, we have got the annual power generation of 3,52,000 kilowatt, which is almost 68% of our energy consumption of McCallum. Now let's compare the results of different simulation software. My fellow team members already discussed about the analysis in Homer Pro and PVWatt. In Homer Pro, considering the annual consumption of this location, we were able to generate about 3,65,000 kilowatt power per year, which is almost 68.7% of total consumption. In PV watt system developed by US National Renewable Energy Laboratory, we have got the annual generation almost 343,000 kilowatt, which is almost 6% lower than Homer simulation result. In Homer, we have considered ideal condition, but in real life, we have to consider some losses and weather conditions too. After implementing the same system in Simulink, we have got the generated power 352,000 kilowatt, which is close to our expected result. After analyzing our proposed system in different three simulators, we can say that our proposed system is capable of generating our desired output. This will help to shut down other two fossil fuel generators of this community and supply the remaining power from the PV generation system. Let's talk about the expenses. Setting up a new power generation project costs a lot of money. However, considering green energy, lots of investors and power generation companies are coming forward. We have got our financial estimate from Homer Pro. The bar chart shows that the timeline of the expenses and earnings for 25 years, the expected timeline of our project. From the Homer Pro analysis, we have found the net present cost almost $2 million for 25 years, which includes setting up floating structures, research and development, transportation, and installation of equipment. The levelized cost of energy comes about 44 cents. For maintenance and operation, the simulator expects the total expense of $1 million, which includes repairing, replacement of panels and machineries, and cleaning of PV plates. All in all, the expense is really high, and for the inflation it may rise more. But we are planning for more optimization to reduce the expense in future. In conclusion, we can say the environmental benefits should get more preference for the clean energy projects. Talking about some good sides, this project can cover up almost 69% of annual power consumption for this area, which is enough to shut down the two of the three diesel generators of this area. The annual fuel consumption as well as the transportation cost will reduce abruptly. It can also be said that this PV powered plant can work as a backup of the diesel generator breaks down for system fault or natural calamity. No doubt, less burning of fossil fuel will produce less greenhouse gas, which will be helpful for the biodiversity of this isolated island. And as the solar panels will be kept on floating structure on seabed, this will not cover up lands and there will be no expense. Considering the benefits, there are also some drawbacks, like this project costs a lot of money and it will be tough to find investors for this project. As the floating solar structure will be on seabed, so it may hamper marine biodiversity and may create some obstacles for the marine vessel or in fishing. Also, during winter, the solar panels will be covered up by snow, which will block the sun rays incident on PV plates. If those are not cleaned and maintained properly, the panels may get damaged and huge financial loss will occur. In future, we have planned to do some more works in this project. We need to develop a detailed Simulink model where we will add battery sizing and protection system. Moreover, we need to optimize our system more to reduce the expense and get more efficiency. We will also work on diesel generator, collect some real-time consumption data and optimize the generators according to the load. This will reduce the fuel consumption and also the inventory cost will reduce in a large margin after all of these optimizations. Thank you so much for listening us. We would like to thank Professor Dr. Tariq Iqbal for his valuable support and guidance during our research work. If you have any concerns and suggestions, please let us know. Thank you.